Hello my dear students, I warmly welcome you to CR Digital Classes. So in this lecture, we are going to discussing about one of the important method, and this method is very important for the long answer purpose for the upcoming examination. Okay. So and this is the last method in the system of solutions of the linear equation in one variable. Okay. So see the statement of the problem first of all. Method is Muller's method. Using Muller's method, find the root of the given equation x cube minus 2x minus 5 is equal to 0 between 2 and 3 and correct to 4 decimal places. Okay, so this is the problem. So by using the Muller's method, we have to find out the real root of this polynomial. Okay, x cube minus 2x minus 5 is equal to 0 in between 2 and 3. Okay, that the resultant root we have to express in the 4 decimal places. Okay, just remember that value. So far we discussed that the bisection method, the iteration method, false position method, Newton-Raphson method, generalized Newton methods. Okay, so far we discussed these 5 methods. Okay, these 5 methods dealing with only one variable. Those all are linear. Okay, so and now the 6th method, so that is Muller method. With this method, the linear equations in one variable process will complete. Okay, then we can go to the non-linear equations. Okay, in one variable. So therefore now you can see here the solution of this Muller's method. Given equation is x cube minus 2x minus 5 is equal to 0. Now to find the root of this equation by using Muller's method, so we need to go through 5 steps. Okay, so here in step 1, let f of x is equal to x cube minus 2x minus 5. Okay, so the given equation we are letting it as f of x. Be a polynomial of third degree. You know very well. Okay, now by Muller's method. Okay, in this method, whenever you are going to solve, you are going to find a root of the given equation. So we have to assume 3 points. Okay, 3 points. So therefore let x suffix I minus 2 comma y I minus 2 comma x suffix I minus 1 comma y suffix I minus 1 and x suffix I comma and y suffix I be 3 distinct points on the given curve y is equal to f of x is equal to x cube minus 2x minus 5 is equal to 0. Okay, on this curve, okay, curve or line, whatever it may be. Okay, so on this curve, so we have to take 3 approximation points. Okay, those 3 approximation points you can take in this format: x suffix I minus 2, okay, comma y suffix I minus 2 and x suffix I minus 1, y suffix I minus 1. So in this format, x suffix I comma y suffix I. Okay, after taking these 3 points, okay, now where x suffix I minus 2, x suffix I minus 1 and x suffix I are approximation to root of the given equation f of x is equal to x cube minus 2x minus 5 is equal to 0. Okay, so whatever we are going to finding the required root. For that required root, this x minus I minus 2, x minus I minus 1, x suffix I, these 3 are the approximation roots. Okay, so in the problem we are going to find out the required root in between 2 and 3. Okay, so in between 2 and 3. So the required root exists in between 2 and 3. Either it is 2 point something, okay, less than the 3. So now we are going here we are taking that. Now here we are taking that the approximation roots x suffix I minus 2, x suffix I minus 1, x suffix I, as you can see x suffix I minus 2 is equal to 1.9. 1.9 means here it is. Okay, so for example, if you extend this real line, okay, so 1.9 is here, 1.9 and x suffix I minus 1, x suffix I minus 1 is 2. This 2 is x suffix I minus 1 and x suffix I is 2.1. Here you have 2.1. That means for the required root, okay, existing between 2 and 3, for the first value 2, we are taking the left neighborhood and right neighborhood values as the initial approximation values. Okay, so for 2, left neighborhood value is 1.9 and for the 2, right neighborhood value is 2.1 and the 2 itself as we have taken as x suffix I minus 1. Similarly, y suffix I minus 2 is equal to minus 1 into 9.1, y suffix I minus 2 is equal to minus 1 and y suffix I is equal to 0.061. Okay. So here also we are taking that minus 1 left neighborhood and right neighborhood as the initial values. Okay. So therefore, this is total about step 1. Now in step 2, by forward difference operator we have in the next unit, that is interpolation, second unit. Okay, in that unit we are going to study that the forward difference operator, that is delta. Okay, so delta, the formula for the forward difference operator is delta suffix I is equal to y suffix I minus y suffix I minus 1. So here you know very well y suffix I value and y suffix I minus 1 value, substitute them, you will get delta suffix I value 1.061. Okay, what is the use by finding this forward difference value? Okay, so we are going to use these values in the general approximation formula by using Muller's method. Next to delta I minus 1, same delta I minus 1 is equal to yi minus 1 minus yi minus 1, y minus I minus 2. So therefore here whatever the suffix value is there, next in RHS, that is the suffix starts with the y coordinate. Okay, so therefore delta suffix I minus 1 is equal to y suffix I minus 1 minus y suffix I minus 2. So therefore that is equal to minus 1 minus of, so substitute those values, then you will get delta suffix I minus 1 is equal to 0.941. Okay, so next we have to find out the value of h suffix I. Okay, this h suffix I you know very well the formula. Okay, x suffix I minus x suffix I minus 1. Okay, in the second unit also we are going to see that formula. So substitute x suffix I value 2.1 and x suffix I value 2 from the given consideration. So therefore h suffix I is equal to 0.1 is the value. Next x suffix I minus 1 is also formula x suffix I minus 1 minus x suffix I minus 2. If you substitute the values and simplify, then you will get the h suffix I minus 1 is equal to 0.1. Okay, same h suffix I and h suffix I minus 1 have the same values only because it denotes the interval. Okay, length of the interval. So therefore that is the step 2. In step 2 we find the values of the forward difference operator delta suffix I and interval, length of the interval h value, h suffix I values. Okay, so in step 3 using Lagrange's formula we obtain a second degree equation. Okay, passing through the above 3 points. Whatever we have considered, above 3 points is nothing but x suffix I minus 2 comma y suffix I minus 2 and x suffix I minus 1 comma y suffix I minus 1 and x suffix I comma y suffix I. Okay, so we have considered these 3 points now. Okay, now by using the Lagrange's formula, Lagrange's equation, we are going to take a second degree equation passing through these points. So that is L of x. Okay, L of x is equal to x minus xi minus 1 into x minus xi by xi minus 2 minus xi minus 1. So the total value. Okay, this total equation represents the Lagrange's equation. Okay, Lagrange's equation. If you simplify that equation, you will get a second degree equation. Second degree equation is nothing but quadratic equation. So clearly you can see here second degree equation passing through the above points is, okay, so the resultant quadratic equation will be in the form, okay, whenever if you substitute those values and respectively xi value, yi value, x suffix I minus 1 value, y suffix I minus 1 value, if you substitute all those values in that equation and if you simplify, then you will get a resultant quadratic equation. That quadratic equation exists in this format. Okay, L of x is equal to the total RHS will convert into capital A into x minus xi whole square plus b into x minus xi plus yi. That is the resultant quadratic equation. This is the general procedure. Okay, so I am writing the general procedure equation for your understanding purpose only. Okay, so why we are using those delta suffix I and why we are using h suffix I values, for your understanding only I am writing these equations, where you can see capital A is equal to, okay, here you have, for this capital A you have one formula. That formula here I am writing. Okay, capital A is equal to 1 by h suffix I minus 1 plus h suffix I into delta suffix I by h suffix I minus delta suffix I minus 1 by h suffix I minus 1. That is the formula. You have to by heart that formula whenever you are going to solve the problem based on the Muller's method. Okay, so this A and this B values plays key role. Okay, so therefore next for B you have the formula delta suffix I by h suffix I plus a into h suffix I. So these two values you have to by heart. Here you can see you have delta suffix I value and here you have h suffix I value. For that purpose only we derived those values in the advance only. So therefore now you can see that now substitute those values. So therefore capital A value is equal to that one. So if you substitute the respective values, okay, so therefore you will get capital A is equal to 6. Okay, so if you simplify with the scientific calculator, you will get that capital A is equal to 6. And next you take capital B equation and substitute the corresponding values in that capital B, then you will get that capital B is equal to 11.21. 11.21. Here you can observe that sign of capital B is positive. Just remember that word. Okay, sign of capital B is positive. There is no negative symbol. So therefore that is a step 3. In step 3 we take Lagrange's equation, okay, of 3 points. Okay, if you simplify that equation you will get a quadratic equation. Okay, in that quadratic equation you will get the x square coefficient as capital A and x coefficient as capital B. For capital A you have separate equation and capital B you have separate equation. In that equation we have the delta suffix I and h suffix I values. For them only we are substituting and we are getting those values. A equal to 6 and B is equal to 11.21. That is about step 3. Now in step 4, from the values of A and B, the next approximation x suffix I plus 1 is given by x suffix I plus 1 is equal to x suffix I plus minus B plus or minus under root of B square minus 4ai by 2a. You know very well the RHS part of equation number 1 is dealing with the one of the formula for the roots of a equation. Whenever you are going to find out the roots of a quadratic equation, that is in the format only. Okay, so therefore minus b plus or minus b square minus 4ac by 2a. Okay, in that format only. Okay, RHS format existing in equation number 1. So here now we need to find out the square root value b square minus 4a into yi. So that implies equal to, so b value and minus 4a into a equal to 6 and here y suffix I is equal to, you have 0.061. Okay, instead of this value substitute that value 0.061 and if you simplify you will get this value 11.14450,986. Okay, previously, so by using this equation number 1 you can see here, since equation number 1 leads to inaccurate results, okay, then we take the equivalent form. Okay, if you use this equation number 1 to solve the root of the given equation by using Muller's method, you will get inaccurate roots. Okay, inaccurate roots. Okay, to avoid that position, so we are taking the equivalent form. Okay, equivalent form of the equation number 1, that is x suffix I plus 1 is equal to x suffix I plus 1 is equal to x suffix I minus 2yi by b plus or minus under root of b square minus 4ayi. Okay, just we are reversing that value. Okay, we are reversing the equation number 1, then you will get this condition. Okay, this equation number 2 gives the appropriate value for the given root. Okay, that equation number 2 gives the appropriate value for that equation number 1. So therefore now by using equation number 2 we can start the iteration to find the required approximation root. Okay, so equation 2 is the general formula. Equation 2 is the general formula for the Muller's method. By using equation number 2 only we are going to start the iterations or approximations. You can see here x suffix I is there, you know y suffix I value and capital B value also you know and a value you know, all values you know. Okay, so while taking that first approximation with I equal to 0, then you will get x suffix 0, x suffix 1 and y suffix 0, y suffix 1. Now you can see here in step 5 we are going to see that iteration process. Okay, so the first iteration, okay, so I am taking x suffix I plus 1 is equal to x suffix I minus 2yi, okay, by b plus or minus under root of b square minus 4ayi. So substitute that x suffix I value 2.1 minus 2 into substitute that y suffix I value 0.061. Okay, and we already derived this value. Okay, capital B is equal to 11.21. Okay, plus and we already derived this value 11.1414. Okay, 50986. If you simplify that value, since the sign of capital B is positive, Why? Because 11.21 is a positive value. Therefore, the sign of capital B is positive. Then you can take that value. Okay. So here you have plus or minus symbol. Okay. In that plus or minus, if you want to take plus, that is depending upon the sign of the capital B only. Okay. Sign of the capital B value. If capital B is positive, then you have to take plus only. Okay. If the sign of the capital B is negative, you have to take the negative. That's why only I clearly mentioned it. Just remember that word. Sign of the value of capital B is positive. So then in plus or minus, we can take plus only, positive only. So if you simplify the total fraction on RHS, so you will get x suffix I plus 1 is equal to 2.09454249. Okay. So that is the first approximation root, x suffix I plus 1. Okay. So error in the above result. Okay. Why? Because we are taking a required root, we have to take up to 4 decimal places. Okay, up to 4 decimal places. But here we have more than 4 decimal places. So definitely there exists some error. Okay, if you find any approximation root, definitely there exists some error. Okay, error in the above result. That error is called relative percentage error. Beginning classes we discussed that relative percentage error is given by epsilon suffix a dash is equal to x suffix I plus 1 minus x suffix I by x suffix I plus 1 into 100. The same formula we also discussed that epsilon r is equal to, okay, so x suffix r dash by x suffix r by x suffix r dash into 100. Okay, both formulas are same only. Okay, for this method we are using, instead of x suffix r power dash, okay, we are using x suffix I plus 1 minus x suffix I by x suffix I plus 1 into 100. Substitute that x suffix I plus 1 value minus 2 into you have x suffix I value by x suffix I plus 1 value into 100. If you simplify that, the error, okay, in this x suffix I plus 1, error is this much of error. A percentage of the error is 0.260555857 percentage is the error. So now you have to do the process to get up to error is equal to 0%. Here we have 0.2. Okay. In the next step 0.1. In the next iteration 0. Okay. To get the error up to 0%, that means there is no error, then the given root is the, then the given x plus I minus 1 value is the required root of the given equation. Okay. Here we are existing that error is 0.2%. Now let x suffix I minus 2 as 2 and x suffix I minus 1 as 2.1. Similarly, y suffix I minus 2 is equal to minus 1 and y suffix I minus 1 as is equal to 0.061. These already existed values only, just we are changing the variable value. Okay, so therefore, and we have x suffix I by using that condition, and we have y suffix I is equal to that condition. So therefore, from this condition, then delta suffix I is equal to, by forward difference operator, delta suffix I is equal to y suffix I minus y suffix I minus 1. Substitute those values y suffix I and y suffix I minus 1. Simplify, you will get negative. Okay, delta suffix I is equal to minus 0.6110036. Next to delta suffix I minus 1. Why we are taking these values? It leads to the second iteration. Okay, these values all leads to the capital A value in the second iteration. So therefore, y suffix I minus 1 minus y suffix I minus 2. So therefore, if you simplify that, delta suffix I minus 1 is equal to 1.061. Next, similarly, h suffix I is equal to, if you simplify values, you will get 0.00545751. Next, h suffix I minus 1 is equal to, you will get 0.1. In previous approximation, we got h suffix I is equal to h suffix I minus 1. Now we got two different values. So therefore, now take capital A value. Okay, that is the direct formula, and substitute the corresponding values and simplify. Then you will get capital A is equal to 6.19454630. Earlier we got capital A is equal to 6. Now we got 6.19. Okay, that is equal to 6.19 means 6.2 something. Next, write down the capital B equation and substitute the corresponding values and simplify 11.1618140. Okay, therefore, earlier we got capital B is equal to 11.21. Now we get capital B is equal to 11.1 6. Okay, 11.16. So therefore the value is decreasing here. So therefore now take that square root value. Okay, so in original approximation we have square root value b square minus 4a yi. So this is the b value we get in this approximation, minus 4a value and yi value. If you simplify that value, you will get 11.16195242. So that is the square root value. After getting that capital A value, capital B value, and under root of b square minus 4a yi value, and delta I h suffix I, after getting all these values, next go to the second iteration. Okay, so directly. So therefore h suffix I plus 1 is equal to x suffix I minus 2yi by b plus or minus under root of b square minus 4a yi. So therefore h suffix I plus 1 is equal to, substitute that value, h suffix I 2.09454249, that is the x suffix I, and minus 2 into what is the y suffix I value, we got that value, and capital B value we got, and this total square root value already we got here. Okay, so therefore substitute all the corresponding values what we have got in the previous iteration. So therefore if you simplify them, now x suffix I plus 1 value you will get in this format. X suffix I plus 1 is equal to 2.094555148 is the x suffix I plus 1. Okay, so in the previous iteration, first iteration also we got the same, approximately same value, where also 2.09 something, here also we are getting 2.09 something. That means you can realize that the required root is existing in the form of 2.09 something. Okay, so therefore now in this value you have to find out the percentage error. Okay, so therefore the relative percentage error is given as epsilon a square is equal to that value. Substitute the corresponding values and simplify. Here the error is decreasing. Okay, so therefore 0.0042921. Okay, that is the error. Error is gradually decreasing. In the previously we got 0.2 percentage error. Now here we got 0.004. That means it is decreasing gradually. Next, let okay, for the third iteration we are considering these values. Xi minus 2 is equal to 2.1 and xi minus 1 is equal to 2.01 and xi is equal to 2.09. All values we got in the previous only. Okay, here we got x suffix I plus 1. The same value here we are taking as x suffix I only. Okay, and initially this 2.1 we have taken as x suffix I. Now we are taking it as a x suffix I minus 2. Just be careful while applying the values. Next, yi suffix minus 2. Initially this value we have taken as y suffix I 0.061. Now we are taking it as a yi minus 2. Next, yi minus 1 value you know very well, yi value you know very well. So therefore from this condition delta I is equal to yi minus 1. Substitute the values and simplify those values and you will get delta I value, and delta I minus value you will get in this format. After getting delta I and delta I minus 1, go to h suffix I, you will get this value, and h suffix I minus 1, you will get this value. Okay, so after getting delta i's and h suffix i's, take the capital A equation. Okay, and substitute the corresponding values, you will get capital A is equal to 2.9314. Okay, earlier we got 6.19. Now here we got 2.93. Why? Because the values what we are substituting are very less value. So therefore next capital B is equal to, that is the equation. Substitute the corresponding values and you will get capital B is equal to 13.16576606. Okay, that is a capital B value. Here capital B is increasing. Previously 11 point something is there. So now 13.16. So therefore now find out the square root value. Then you will get here 13.165766607. So after finding the delta suffix I, h suffix I, capital A, capital B values, take the third iteration and substitute the corresponding values in that equation. Then you will get, if you simplify them, if you get x suffix I plus 1 is equal to 2.094555148. Okay, x suffix I is equal to 2.094885148. So therefore the error in the above term, for that value, for that x suffix I plus 1 value, you have to find out the relative error, percentage error, that is given by, if you calculate them. Okay, so therefore error is 0%. There is no error in this value. Okay, so in this value, in the equation number 3, there is no error. So clearly we can say that equation number 3 is the required approximate root of the given equation. Okay, x cube minus 2x minus 5. Therefore, there is no error in equation number 3. So, therefore, the required root is x suffix I plus 1 is equal to 2.094555148. Okay. Hence, the required root of the given equation correct to 4 decimal places between 2 and 3. మనకేం అడిగాడు ప్రాబ్లమ్ లో? సో రిక్వైర్డ్ రూట్ ని correct to 4 decimal places అడిగాడు. Okay, therefore from this condition you can take that. So 2.094 up to here 2.094 is the 3 decimals. Now by using these values you have to write down the fourth decimal. So fourth decimal you can write 4. Okay, so why? Because 5 those all are the half greater than half of the unity. So therefore you can write 2.0946 is the root which is existing between 2 and 3. Okay, so it is existing between 2 and 3. So therefore you can take this value as 2.092 is there and 3 is there. So this is the process to find a real root of a given equation by using the Muller's method. This method consumes a lot of time in the examination, and majorly these type of problems based on the Muller's method, they will ask in the long answer purpose only. Okay, so whenever you are going to start the proof of this method, so just be aware. If you know the other questions, then go for them. Okay, so or if you do all other questions in long answers, then come to this question and at the end of the examination. Why? Because if you start the beginning of the examination, okay, so this question consumes a lot of time, so then you will get little bit tension while solving the answer. So therefore start this type of problems. If you get the examination question paper, okay, start this type of question papers as much as late. Okay, and one more thing is we are discussing rate of convergence for each and every method. Okay, so now here rate of convergence of this method is capital P is equal to 1.84. For the Muller's method, rate of convergence is P is equal to 1.84 is the rate of convergence. In the previous lecture we discussed that Newton-Raphson method has quadratic convergence. Like that only for Muller's method, rate of convergence is 1.84. Next, we'll have another method, Chebyshev method. That is not exist in your syllabus, but Chebyshev method has cubic convergence. Okay, or convergence as order 3. Okay, so this is about this total Muller's method. Prepare well, make a perfect practice. Until bye, thank you.